Decision Analysis, Session 5. In this program, I'll demonstrate the use of the Excel tools to complete the Session 5 team homework problems from Chapter 14. I'll also be highlighting key concepts and terms that are given in the chapter. So let's begin by looking at Problem 5. In the Sakai Resources folder, Chapter 14, the Excel tool, problem 14.5, can be found. So we're looking at an Excel sheet labeled payoff matrix. And this is for problem 5. Philip is investing $30,000, and he can either go with stocks or a CD. Now the stocks vary in performance, of course. And the payoff matrix will show the payoff for stocks under good, average, or poor conditions. The CD investment stays constant. So for any of the conditions, it's an 8% payoff. Now once we input our payoff matrix, the Excel tool will take us through the different techniques for making a decision. Here we're trying to decide stocks or CDs. So if we look just in terms of the maximum return, stocks would be our choice, and the Maximax technique is showing us that. So the highest that we can get here is 16%, and that's what this table shows. The next table will show us the kind of worst case scenario. So if we had the best outcome under the poorest conditions, we can see that the 8% or the CDs would be the correct decision here according to that decision rule. Looking at regret, the regret considers the opportunity that is lost. So the regret matrix is a little bit different than a payoff matrix. Here, let's consider where the 0 comes from. So we would have 0 regret if we invested in stocks in a good economy. Why? Because in a good economy, that pays 16%, and the CD pays 8%. So the maximum of those two is 16%. And if we made that correct choice of investing in stocks in a good market condition, we would have 0 regret. But if we invested in CDs, we would have an opportunity loss, or a loss of the opportunity to earn that other 8%. To minimize that regret, CDs would be the correct decision. Because if we made the worst choice here, putting all the money in stocks under poor market conditions, we would lose the opportunity to earn 10%, and we can minimize that by making the decision to invest in CDs. But these outcomes are also going to vary according to the probabilities of each of the 3 market condition categories. So in Chapter 14, that's essentially what we're doing. We're looking at ways of tabling different sets of outcomes. But we also want to consider the probabilities of each of those outcomes and weighing all of that information in the correct proportion, because some things are going to happen more frequently and some things are going to happen less frequently. We can use some basic techniques to make a better decision. So here we're computing the EMV, or the expected monetary value, of the investment choice that Philip is trying to make. So here, the 9.2% gives us the expected payoff over time, because some of the time, 10%, will have good market conditions, and if we were in stocks, we would get 16%. 85% of the time we'll have average conditions, and then we would be earning 9%. And so on. If we had a poor market, we would be at a loss of negative 2%, but that's only occurring 5% of the time. So the weighted average for stocks shows 9.2%, which is better than that constant 8%. So the expected value 9.2% tells us to make the decision to invest in stocks. Now, what is the value of the perfect information? So if we're always right, we would be in the correct investment at the correct time. So using a simple max analysis, we can see we would want to be in stocks because it's more than CDs when the market conditions are good and average. But we would want to be in CDs in a perfect world if the market conditions were poor. So weighting those three ideal outcomes tells us that in a perfect world, we would be expecting about 9.7% return. And we computed that as a simple weighted average of what we could get in a perfect world. The difference between our perfect world estimate and the real world of investing in stocks is only 0.5%. So now if I wanted to figure out the value of that perfect information, I know how much Philip is investing, and I know that it's going to be 0.5% of that investment to get it to a dollar value. We could do the same thing with our regret matrix. Here we're using the same regret matrix that we showed previously, but we're weighting it by the probabilities to get an expected regret or an expected opportunity loss. And we can see that the minimum expected opportunity loss for us is with stocks, and it is that same 0.5%. That value difference that we showed here of 0.5% will always be equivalent to the expected EOL. Now let's take a look at problem 16. Problem 16 is a simple decision tree problem. And decision trees give us a way to show visually a series of outcomes that depend upon one another. So here in problem 16, we're looking at three different tests. And the tests have to run in sequence. So they're labeled test X, test Y, and test Z. So we're considering and trying to show on the decision tree the different possibilities. So here, if we start with Z, we can pass or we can fail. And there's a probability attached to these outcomes. And we can then go on to test X or Y. And each of those would have a probability of passing and failing. Let's look at an Excel sheet that's going to help us get the information we need to fill in our table. So we have three tests, X, Y, and Z. And each test has a cost. So there are only a limited number of sequences possible. So let's look at a couple of those. If we considered starting with test X, well, if we went straight through and said X, Y, Z, we passed them all, of course we can see simply by summing our costs that the cost of the sequence would be $6.15. And it would always be that cost if there was no probability of failure. But because there is probability of failure at each of these steps, x, y, z, if we fail x, we're finished. And then that sequence would only cost $1.75 because we couldn't move on to y and z. Similarly, if we passed x and passed y, but then failed z, we would not always incur the same cost over time for that sequence as well. So what we're going to do is consider the probability of failure using the sequence x, y, z as an example. So we already know that if we go straight through, that we are going to incur the cost of $6.15, but we wouldn't pay that on average for a test run because of the probability of failure. So here you can see that I'm taking that $6.15, but I'm weighting it by the probability of passing test y. And I get about $5.69. Now, if I pass y, I'm going to incur the cost of test z because I'll go on in sequence. But I'm not always going to pass test y. And if I fail, the cost is only $3.75 because I'm only paying for x and y. So here, the probability of failure, or 0.075 for test y, is used to weight the $3.75, which would be our cost for only the tests x and y. When I add those together, I get the weighted average for the XYZ run going from X to Y. Compare that to the $5.87 if I go from X to Z. So it seems that going in the sequence XZ of these two possibilities, and we could show that on our tree, going from X to Z seems better because it's cheaper on average. But this still doesn't consider and weight the effective cost, total cost, considering the probability of failing test X. So we're working all the way from back to front, the $6.15 all the way back to the first step of running test X. And the 587 we already know is the minimum of these two. So $5.87 is what we're going to pay when we pass X, which we're going to do 87.5% of the time. But if we were to fail test X, we would only pay $1.75, and that's going to happen the other 12.5% of the time. So considering all of our information for the sequence X, Y, Z, we would get an expected cost of $5.35, and we can fill in all of this information on our decision tree. We could then repeat these steps for the other sequences if we begin with Z and go to Y or go to X, or if we begin with Y and go to X or go to Z. How would that affect our expected costs? The minimum cost, of course, would be the correct decision and the primary answer to our problem. Now let's take a look at problem 21. Problem 21 is a very good example of how simple decision trees can be. We have a situation where we have two competing companies, SGC and NGC, and they're both making bids for a drilling site. And SGC is trying to decide whether they should bid high at 16 million or low at 7 million. So I've given you a couple of tools for problem 21. I've given you a blank decision tree. If you would like to try your hand at generating some of these Excel calculations but I've also given you one with those calculations on them. So in effect, I've given you part of the solution, and I've done that so that you can have a functioning Excel sheet that allows us to focus a little bit on sensitivity analysis. So the decision case here is pretty straightforward. And the high bid of 16 versus the low bid of 7. So let's look at, first of all, what happens if SGC bids high. Well, they're going to win the bid because NGC either bids 10 or 6. Okay, so their bid's going to be highest, and so NGC is really not a consideration in that event. So the high bid is going to win. Then we only have to consider payoff. The payoff varies according to, this is a drilling site, so it's going to return a certain amount of resources, and that's going to be valued. So if that's a large payoff, 120 million, average 28 million, and of course if the site is unusable, it's not going to generate any payoff. But there are still costs, and you can check those in the problem, and these costs are considered in coming out with our payoffs. But now we're going to use that expected value, that EMV we looked at earlier. So simply by weighting the payoffs by the probabilities that are given, we can get that expected value, or that expected monetary value, payoff, of bidding high. So if SGC bids high, they're going to win the bid, and they are going to, on average, or they could expect 6.8 million, at least considering the probabilities. And that answer is dependent upon those probabilities. On the other hand, they can bid low, 7 million. And if they bid low, now they're competing, and 40% of the time they would lose the bid because their competitor would bid more. But 60% of the time, at least that's their estimate, there's a 60% chance that NGC is going to bid low, which is only 6 million, in which case SGC wins the bid again. So there's no payoff if they lose the bid, and we can see that on the decision tree. Our attention needs to go here if they win the bid. And so considering costs, the payoffs have been calculated for each of the three outcomes: large, average, or unusable. The weighted average of these three, what would be the EMV, is really not what we could expect all of the time. If we simply use a weighted average here, we get the 15.8. And that's probably not a good estimate, because that's only going to happen at a 60% probability. The other 40% is also a factor here. Okay, so 0.6 times that weighted average for winning the low bid. The difference here is pretty significant. It takes us down to 9.48. But nevertheless, the 9.48 based on the low bid is greater than the 6.8 based on the high bid. Now, while the previous analysis would certainly be helpful, as we noted, all of our results are based on probabilities, and we use sensitivity analysis to sometimes make strategy tables which will show us different decisions if the probabilities were to change a little bit. So the probability being considered in Part C is the probability of NGC bidding 10 million, which is currently set at 40%, and their low bid of 6 million at 60%. So what we want to do is to see how sensitive our decision would be to NGC. What if there were a 50-50 chance? Well, our decision would still be to bid low because the 7.9 expected is still greater than the 6.8. By varying that probability, we can complete the table on the worksheet Part C. And then finally, to complete problem 21, another good reason for providing you with a working spreadsheet is that you can do more thorough sensitivity analysis. Here, what you're trying to do is to vary the expected value of the large strike versus the average. So right now, it is set at 120 million and 28 million respectively. So we'd like to change the large to 100 and the average to 20 to see how that would affect our decision to bid high or low. The highlighting on the table should direct you in terms of what outcome you should be looking for. This concludes the video demo of the Excel tools for decision analysis session 5.